This is the second part of the presentation about word2vec. Let's go back to the idea of using co-occurrence matrices to represent word. If we use that idea, we remember that we will have a very long and sparse vector for each word. Why is that the case? First, we see that in co-occurrence matrix, the length of the vector equals to the size of the vocabulary. So you usually have a lot of words in the vocabulary such that your vector will also be that long, which is very long. However, in that long vector, you usually have a lot of zeros in it because a lot of words, they don't usually occur together. Like for example, cherry and aardvark, they never appear together in our data set, so the value is 0. And then you also have a lot of zeros, zeros, and zeros. So it's called sparse vectors. We actually prefer vectors that are short. Perhaps the dimensions is just 50 or up to 1,000. And then we also prefer dense vectors. By dense, I mean that most values in the vectors are not 0. The reasoning behind that preference is that first, when we use these vectors as the features in machine learning systems, usually shorter and denser vectors perform better. So now you may think that these vector of a word become the feature of the word. So word is a data, and then the vector that represents that word is the feature. And then if you think about, for example, logistic regression, where you have to learn the weight for each feature. Now, let me ask you, which is easier, learning the weights of 100 features or learning the weights of 50,000 features? Of course, 100 is easier because to learn 50,000 features accurately, you may be able to do that, but then you may need a lot more training data to get the correct weight for each feature. But then when we have smaller number of parameters in our model, so in regression, let's say when we have fewer number of variables, usually it may generalize better to the test set or the data that we have not seen before. Remember, when we have too many parameters, when the model is over complex, then usually it will not generalize better to the other model because it overfits the training data. So to summarize why we like this word2vec approach is because it results in a shorter and denser vectors, such that when we apply it to machine learning systems, it is usually more successful and it avoids overfitting. Now let me introduce the terms target word and context words. Before going there, let's see how we usually analyze a sentence. In analyzing a sentence, usually we will use a window which is called a sliding window. So let's say that is the first window that we use in the sentence, and then we slide it one word to the right. We slide it again, until finally the window reaches the end of the sentence. Why do we need this sliding window? Well, usually the word in the middle of the window is called the target word. And then the other words to the left and to the right of the target word is called the context words. Here the sliding window is plus minus 2. It means that anytime you have a target word, you slide 2 words to the left and 2 words to the right. word2vec is a supervised machine learning classifier. If you think about the example in the supervised machine learning that you've already learned before, think about the example where, let's say, you have 100 customers. You have the set of features for each customer, and then you have the label whether the customer wants to buy a boat or not buying a boat. Let's keep that analogy in mind while we're looking at what word2vec wants to do. So word2vec wants to train a model that returns a high probability of a context word C that is the actual context word of word T. In this example, the target word or word T is the word apricot in the red circle. And then all the words with the blue arrow are the context words, word C. We want to train the classifier such that it gives a high probability of the actual context word of a word T. So here, tablespoon is actually the context word of apricot. So the model should also give a high probability for that. Of is a context of apricot. So we want to have a high probability saying that yes, the word of is the context of apricot. The same thing for the word jam and the word a. So in other words, we want to see a high probability of the actual context words being classified as the context word of the target word. So given the pair of target word and the context word, we want to have the model that returns the high probability of the label as positive. Positive label means that yes, that context word is the actual context word of the target word. So we want to have a high probability of probability plus, given the apricot and tablespoon. We want to have a high probability of plus, given the pair of apricot and of. Now, we also want to have a high probability of other words being classified as not context word. Okay, so let's say I have a random word aardvark. You know that this is not the context word of apricot. So we want the model to have a high probability of saying that the label is negative when we have the context is aardvark and the target is apricot. So in other words, you want to say it is very not probable to have the word aardvark as the context of the word apricot. So going back to the example of customers buying a boat or not, so what we want to see here is if the feature is correct, you want to say that, okay, the customer is very likely to buy a boat. If the feature is wrong, not really wrong, but if the feature is not, it's not suitable with the pattern in your training data, you want to say that most likely that customer will not buy the boat from us. So it's similar here when you have the words that are actually context and target words in the sentences that you have seen. You want the model to return a high probability for saying that, yes, that is the context word of that target word. But if you've never seen that pair of words before, like aardvark being the context of apricot, you want the model to return a high probability saying that, no, it is not likely to become the context word of the word apricot. Aardvark is not likely to become the context word of apricot. So now you know that, okay, if a word is the actual context word of a target word, then the model should also be able to say, yes, that is the correct target context word. If the context word never appears with the target word together, then the model should also say, no, that is not likely to be a context word. Yes, we know what we want to do, but how can we do that? Well, word2vec use this skip gram intuition. In this intuition, it says that words that often occur together in a window, they should have similar embeddings. So let's say tablespoon and apricot, they appear together a lot, so this intuition says that their vectors should be similar. The vector of the word tablespoon, the vector of the word apricot should be similar, according to this skip gram intuition. Okay, so we know that the words that occur in the window together should have similar embeddings. How do we measure the similarity between two vectors? Well, we can say that using the cosine similarity that we've seen before, the similarity of two vectors is proportional to the dot product of two vectors. Let me give you an example here. Let's say we have the word apricot. We have the word jam and the word aardvark. So by the way, aardvark is an animal. This is what we would like to have. The vector of apricot is pretty close or pretty similar with the vector of the word jam. So T is target word, C is context word. Why? Because we have seen in the documents that apricot and jam, they do appear together, and then jam is the context of apricot. However, on the other hand, we never see or we rarely see aardvark and apricot appears together. So the vectors for apricot and aardvark, they should be not pointing to the same not pointing to the similar direction. They should be very different. So this is what we would like to have. And then let's say we want to compute the similarity. For the apricot, I just make up like numbers. So apricot, let's say I have this vector is 3 and 0. So you can imagine in the x-axis it goes to 3, and then in the y-axis it has 0 value, while the vector jam, the x-axis is 3 and the y-axis is 1. So you get the dot product here is 9. However, in the case of the word apricot and aardvark, again, I'm just made up these numbers, but just to show that the dot product is much smaller than the similar vectors. So here we can see how the dot product may reflect how similar two vectors are. And this is the example of what we want. If jam is actually the context word of apricot, we want the vectors to be very similar. If aardvark is not the context word of apricot, it's not, then we want the vectors to be very dissimilar as well. Now, when you have the similarity, the value is ranging between plus infinity to minus infinity. But what we want here is the probability. How can we convert numbers into probability? If you remember our discussion about logistic regression, you can use the sigmoid function. How can you do that? So if you have two vectors, the vectors for the target word T, you have the vectors of the context word C, and then you may use this sigmoid function to define the probability that the model saying, yes, C is the context word of T, using this formula here. So using this formula, you may see that if you have the vector for T, if you have the vector for C, you may compute what is the probability that C is classified as the context word of t. If you're still not very convinced of how this works, you may just plug in this number here to the t and the c. You will see that the more similar vectors will yield a higher probability of being classified as positive. On the other hand, if you plug in these numbers, these vectors are very dissimilar to each other, you will certainly get a much lower probability. I strongly suggest you to try with the numbers such that you may experience that, oh, okay, so this is how we get the probability of being labeled as plus given the context word and the target word. So let me recap what we've had so far. So given the sliding windows, we have a lot of target words and we have the corresponding context words to those target words. We want a model to be able to say that if you often see the context word C and the target word T appear together, you want the model to give a high probability of saying that yes, C is the context word of T. If you rarely or never see them appearing together, the context word and the target word, you want the model to give a high probability of saying that no, C is not likely to be a context word of T. Now, how can you say that if C is the context word of T, how can you say that they should be similar? It calls the skip-gram intuition, which says that the vectors of C and T should be similar if they often appear together. And to measure the similarity, we use the dot product or the cosine similarity. However, from that result, to get the probability, we use the sigmoid function. Now, so the job that we have here is that we need to get the vector T, get the vector C, such that for the correct pairs, the similarity between T and C is high. And for the wrong pairs, or the pairs that never appear together, the similarity between T and C should be small. Now, what is T and what is C? T is the vector of target words. C is the vector of context words. So the job here is that we have to find the value for vector T. So let's say the dimension of the vector T is 100. We have to find the value of each dimension in the vector T. So how can we do it? As in the logistic regression, we also start with initial set of embedding vectors that we set up randomly. It means that, let's say for the word apricot, you just randomly make a vectors of, if you have decided that you want the length to be 100, then you just randomly set a vector like 3.17, 2.6, minus 110.3, and so on. So you just start with random vectors for all words. Then what word2vec does is that it iteratively shifts the embedding of each word. The embedding means this vector of each word to be more like the embeddings of the word that occur nearby in the corpus. So if the word apricot and jam appears together a lot, word2vec will shift the vectors of apricot and jam to be more similar. However, if the word apricot and the word aardvark, they rarely appear together, then word2vec will shift the vector such that they will be more or less likely to each other. How can we shift the value of a vector? Let's say initially we randomize the value of 3.17 for the first dimension of the word apricot. How can we shift this value to become closer with the value in the apricot vector. Same is in logistic regression, we use gradient descent. If you think about the supervised learning context, you have to have data that are labeled as positive and labeled as negative. Let's look at the window here. In the window here, the target word is apricot, and there are 4 context words: tablespoon, off, jam, and A. So this window provides 4 positive examples. Tablespoon is yes, the context word of apricot. Off is also yes, a context word of apricot. Jam is also yes, a context word of apricot. And A is also a context word of apricot. However, in order to learn something, as I said before, you need negative examples, the words that are not the context word of apricot. How can we do that? In word2vec, the method usually picks the other words from the vocabulary using a weighted random scheme. So they have a scheme that it takes the word randomly, but is weighted, for example, by the frequency. So let's say if the word my appears a lot more in the dataset, then it will have a higher probability to be picked here. But the point is, for the negative examples, you just pick the other words from your vocabulary and then label them as negative. It means that these words are not the context words of apricot. So now you have positive examples from the windows above, and then you have negative examples. Now you may do the learning of the vectors such that, like the skip-gram intuition says, the words that appear often in the same context will have similar embeddings. So same as learning the weights in the logistic regression, there are 2 main components to learn the vectors in word2vec. So the first component is the loss function. It tells us what to maximize or what to minimize. Well, if you just take the minus of this function, then you minimize the function. But here we are maximizing this loss function. So loss function basically tells us how far we are from the correct label. If we are still far, then the second component, gradient descent, will shift us a lot to the direction where we're getting closer to the correct label. If we are already pretty close with the correct label, then the gradient descent will still shift us just a little bit. Now let's take a look at 2 examples here. We have positive examples and negative examples. For the positive examples, let's say the target is apricot, and then the context is tablespoon. We know this is a correct pair. So to get the similarity between them, we just take the dot product of tablespoon and apricot. Now, what about the negative example? Here we can see that to maximize this loss function, we would like to have a high probability of the model saying that no, this word is not the context word of the target word. How can we do that? Saying that N is not the context word of T. Well, here it says that you can just take the dot product again, but just put the minus in front of it. Let's see how it works with the example of apricot and aardvark. Suppose I have 3 vectors that represent aardvark. So you see the first vector is quite similar to apricot, the second becomes less similar, and the third one becomes very dissimilar. So if you take the dot product of these 2, the value is 9. If you take the dot product of these 2 vectors, the value is 3. And then if you take the dot product of these 2 vectors, the value is -9. Now, by taking the minus sign here, you see now the most favorable, okay, let's take the minus sign. 9 becomes minus 9. 3 becomes minus 3. Minus 9 becomes 9. So now this one has the largest value. If you want to maximize the loss function, this is the best. Let's see why that is the case. Well, because the vectors are very dissimilar, the dot product is very negative, then we take the negative of the dot product. So now it becomes the most positive of all, so it supports what we want in the loss function. We want to maximize the value of the loss function, so this is the most positive. The most positive value here represents the most dissimilar vectors, which is actually what we really want. So to recap, in a positive example, you just calculate the dot product between C and T, and then for the negative example, you calculate minus the vector of the context word multiplied by the vector of the target word. And that's the function that you want to maximize. So finally, let's take an illustration here. So word2vec have a set of vectors for the target words. It also have another set of vectors of the context words. But of course, the words itself may appear in both target words and context words. For example, you have apricot here in the set of target vectors. It also actually appears here in the set of context vectors. Because if you slide the window, sometimes apricot is the target words, another time it's a context word. So here, based on these two sets of vectors, each time you will compute the similarity between C and T here. C and T for the correct pair of context and target words, and then N and T for the pairs that are actually not context and target words. What you're going to do here is that you will keep increasing the similarity between the correct pair of context and target words, and you will keep decreasing the similarity between words who are actually not the correct pair of context and target words. So here finally word2vec will return this set of vectors as the word embeddings of the words in the documents. So I will not ask you to derive all the computation or to code the gradient descent, but I think I will give you an assignment on practicing the word2vec package in Python, so you know at least you can see the results. Now, if you have any questions, as usual, leave your questions in the comment section, or you may also go to the IDE in the Q&A forum. You may ask questions, and the other students may also answer those questions and have a discussion. So that's the end for this topic. Thank you.